Hello. 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 What? Will you release assignment 2? Not yet. Talk about that.
My pain, take the space in my life.
All right.
Oh, really? It just lottery schedule?
Well, one thing, right, that was a song we played before the lecture. In a lot of moments in our life, we are just thinking about what the one thing right to do, right? Like, even for this class, whenever there is a poll question, one thing right, what's that one thing right? And today we are going to tell about a lot about this one thing right to do when you are designing your programs. But before, go ahead. I was going to make a joke, but you oh, okay. What was the joke? I mean, just before you said one thing right and the full question, because sometimes there is multiple things that could be right. Oh, yeah, that could be true, right? So, yeah, but at least get one thing right, right? So one thing right, that's important. So today we are going to talk about what to do to get that one thing right when you are designing a program that interacts with your memory hierarchy. Most of the time, your program has to do that. But before we start, it's always a good thing to remind us where we are coming from. So I think you saw this graph many times. So you must remember that now your processor is your Monima architecture is not just processor and DRAM. In between your processor and DRAM, there is something called cache, and to optimize the latency, the average access latency, we make the cache itself multiple labels. So the idea is that the smaller the cache, the faster the access time. If you make the cache larger, of course it can keep more data. However, there is no free lunch. So if you make your cache larger or more with associativity, all this will sacrifice the access time. So it turns out that we have to make it multiple labels in a way that the closer to the processor, the access time could be more aligned with your processor cycle time, so that whenever it's hit in L1 cache, it won't create penalties when you are processing instructions. However, we also don't like the idea that, well, if it's missed in L1 cache, it has to go to the lower level memory hierarchy. So that's why we try to build as many lower levels of cache as possible. And some of you might be asking, well, why don't we have L4, L5? It's all depending on the hardware technology of manufacturing those memory hierarchy. And sometimes, again, if you make the cache really large, the access time is just way too long, so it doesn't make sense to build that. So that's where that's the hardware looks like. And this cache idea works because we have localities. However, there are still cases that we are going to we are going to face the reality that we will have cache misses. And there are three main reasons why we have the cache misses. So the first type of miss is compulsory miss, which means that whenever you start a program from scratch, there is nothing in there in the very beginning. So there must be some miss there, right? So that's one type of miss. And the second type of miss is called capacity miss. It means that the access pattern just needs so large amount of data in a way that we could never put them all together in a short period of time. So that's called capacity miss. And capacity miss, and the third type of miss is called conflict miss. It means that the data you accessed were there before. However, for some reason, it was gone, right? So this is one of the reasons you probably use a lot when you interact with your parents, especially during the Halloween season, right? Like your parents might be interested about like, hey, there were candies on the tabletop. Where we went? Well, it was there before, right? But it was gone for some reason. Actually, you have a magic that all of them go into your stuff, something like that. But well, a little bit off, right? But the thing is that the conflict miss falls into that category. So some of you might be confusing about the idea of a conflict miss and capacity miss. So the distinction between conflict miss and capacity miss is that conflict miss is a phenomenon that comes from the fact that because you have the cache collision or competition about the cache blocks. So if you can change your cache configuration to that, this miss is gone. It's not conflict, but it's not capacity miss. So, for example, if I have two elements that fighting with each other, you only have two elements, but your cache can accommodate more than two elements. So, in a way, it means that if you can change your cache configuration, so both of them can be in a cache at the same time, it's not going to be missed, and that's called conflict. However, if you make your cache fully associativity, means that your cache blocks can go anyway, it's still a miss, that's capacity miss. So these are three different types of miss. And in the last lecture, we talked about how to change, how the cache configurations like A, B, C, these three basic parameters can improve or change the behavior of cache. And the answer, well, is 4. This is wrong. Well, sorry, 3, right? So that was the question that we have been asking. And also, this is actually, as an undergrad student, you should know. And this is something that, as a grad student, you should know, right? So it came up. It turns out that we read a paper by Noam Joby, and Noam Joby said 4 different techniques that you could use to improve the performance of AMD's Phenom 2 processor if you are interested about how this process will go, you can definitely look online and you will see it's a very sad story for AMD. Started a sad story of AMD 10 years ago. And the thing is, but the thing is that for this processor, right, if you can use this for hardware techniques, that will definitely help. So today we are going to continue looking at other hardware optimizations that can help cache performance. But again, this is a computer science class. So if it's an E class, I will probably stop here. But because this is a computer science class, it's more important for us to figure out what's the later part. What, as a software programmer, what you could do. And actually, you will figure out that you are more powerful than those hardware optimizations. But here, so the first hardware optimization that exists now, I will say everywhere in your hardware design is called non-blocking cache. So the first optimization I talk about is called non-blocking cache. But before we talk about non-blocking cache, what's a blocking cache? So by the name blocking, it means that when somebody uses that thing, nobody else can use it, right? So as a software programmer, you must know that blocking call, right? So like when you call a function in general, it's a blocking call because your program cannot be proceeding if the function code is not finished. So that's a concept of blocking. So same thing, if you consider the whole cache access as a function code, blocking cache means that whenever I issue a request, like a block fetch, and if it can only accept the next request after the block fetch has been finished. So that's a blocking cache. And so the access is like this, right? If you don't finish this one cannot proceed. So this is the blocking cache idea. So now blocking cache is this. We try to make the cache more, I would say, like allowing multiple accesses simultaneously at the same time. However, it's from the hardware perspective, it's really complicated to do that because it means that each cell you need to have multiple word lines and bit line to do it. And each word line and bit line is hardware cost. And if you don't have that many chances that you are going to access the same cell in the meantime, it doesn't work to do it. So as another thought to fulfill the goal that we want to allow multiple accesses, and we also find out that there's very rare chance that we are going to compete on the same cell in the meantime. Because thinking about your code, right? Most of the time, if you have spatial locality, you are going to access the memory block instead of the current block. And if it's the current block, it's already in the cache, right? So turns out that this is what we do, right? So we make the cache non-blocking, but instead of making each cell allowing multiple accesses, we organize this memory cells or memory pages or memory blocks into multiple banks. And each bank, you can consider them as an individual unit of access. So whenever you have a block fetch request, it will occupy one bank. And again, the access to this bank is still blocking. So when a bank is performing access, nobody else can still use this part of the memory. However, if another request goes into another bank, then these two access can be performed in parallel because they don't belong to the same bank. So in this way, these two accesses can be performed simultaneously and to save your time. So that's non-blocking cache. And to implement non-blocking cache, there are multiple ways. For example, you can duplicate the word line and bit lines, but that's too much of the cost. So the modern design typically just do this. Just partition your memory arrays into banks. And we perform bank level parallelism
when we are accessing this, performing this request. And if you're lucky enough that the next block is not conflicting with your the bank that is performing access, you still can enjoy the effect of simultaneous accesses. So that's the idea of multi-bank cache and non-blocking cache. So if you have multi-bank cache, right, it turns out that, well, in a path, if we have a blocking cache, if we have a few memory requests, you can only do each of those back to back. But now, once you issue the request one, if it goes to bank one, and the second request when it arrives the cache, and we find out it's not going to the bank that is occupied, we can have that access performed immediately, right? So in this way, you can see originally we have 4 serial requests, but now we can parallelize them in this way. So that's the effect of multi-bank and non-blocking cache. So now, given that you know the idea of multi-bank cache, I just want you to see how this could help us. Well, I do this based on how many have taken. 5, 4, 3, 2, 1. Time is up. Okay, what do you guys think? Let's see. So, looks like you got more time now. Right, so go ahead, discuss with your friend and see what you guys think.
Yeah. Oh, yeah. For the good on the top of there. Yeah. So then after. Oh, so you mentioned. I think it's third one. So you can put down around the That takes only like 3 minutes.
All right. Wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, whoa, looks like everybody is fine with C now. So why don't we just have some of you tell us what do you think? Anyone want to share? Okay. What do you think? Okay, blocking cache. So how much time does blocking cache take?
0, we will issue a request
Okay, 10 nanoseconds.
and for upcoming 3 requests, each request of 1 plus 10. So 1 plus 10 is 11 and times 3.
And take the next request one after. Okay, I guess the wording here is a little bit vague, right? But what I meant to say is that if after I access this is saying that I can send out the next request one nanosecond later. So you don't have to add that 1 nanosecond because this is 10 nanoseconds already.
Sure.
So it's long enough. Okay, so in this way, how does that change your mind?
Yes. Whatever we do, that
Right? So this is like 10 nanoseconds. Okay. How about the non-blocking version?
we can say that 0 is will cost 10 seconds. Time 1 second will cost another. Yeah, so that's overlapping.
Right.
So finally, we will have 13.
Okay, here we go, right? So if you don't have the non-blocking cache and multi-bank cache, this has to be processed in series. So it turns out that it's 40 nanoseconds. And if you can make them bank, it becomes 13, right? So it's very close to 3 in this way. All right? So first of all, right, like if you have the idea of bank, it doesn't allow you to fully parallelize in some sense because there are still some serialization parts, but it's good enough to give you sufficient amount of speed up. So that's why, and the other thing is that the good thing is that you don't have to duplicate the amount of logic to allow parallel accesses. So it's a very good deal. All right. So that's the idea of multi-bank cache. And another thing, right? We talk about the penalty. When we talk about whenever there is a cache miss, right? We kind of like forget that there is also no free lunch whenever you have a cache miss, and then you have to fetch the block from the lower level memory hierarchy. And you might think, well, we have a pretty big bandwidth between each level of memory hierarchy, but the reality is that we don't. So the reality is that the bandwidth between each memory unit is pretty limited. So first of all, the processor, well, typically when we say that we have a 64-bit processor, it means that your processor has registers in 64-bit. And because of that, your processor is designed in a way that we assume every time when you need data, you want to fit it into the processor, is also 64-bit. So your processor has a 64-bit bus between your processor and your cache. So what does that mean is that each cycle you can only get at most 64-bit of data, which is a byte, a double or a 64-bit integer. And again, right, like for your L1 and L2, typically we also follow the same logic to build a 64-bit. Sometimes you have 128-bit bus between your L1 and L2. And thinking about the block size of your is 64 byte, not 64 bit. And you might be asking, why don't we just build 64 byte bus between your L1 and L2? The answer is that, of course, you can do that, but the idea of bus is that every wire has to be synchronous. And the cost of synchronously moving data between two units is really high. And not just the area, the size, the hardware to build it, but also after you build it, there's no way that you can keep this many wires all synchronized in a very short period of time. So it turns out that your cycle time will be really, really long if you make such a wide bus. So in terms of hardware cost, in terms of efficiency, this is not a good idea, right? If you still feel like I couldn't imagine that, then thinking about how many of you have road trip experience of road trips before, right? Like, how easy is it to get 4 people in a car at road trips, comparing with you have 64 people that you want to organize a road trip, and you need 16 cars, and you want to make sure that 16 cars all live together and all arrive at a parking lot together, plus everybody has to find a parking spot. And finally, everyone, when you go on the road trip, everyone has to walk in the same path and in the same pace, and everyone has the same bio schedule, so no one will go to the restroom. So this is like, even for human behavior, it's really hard to coordinate those things, right? So same thing for the hardware. So don't think that hardware is too different from human beings. In a lot of cases, you will figure out how similar they are. So the thing is that we don't build very wide buses between caches for this reason. So the reality is that the bandwidth between each layer is limited. So it turns out if you have an L1 miss, we say we want to write back and fetch a block, right? This is what we want to do. But if you draw it in a time diagram, what would happen is that you will have to write back the first chunk of your block, because, as we said, a cache block is like 64 bytes. But your cache can only write back 8 bytes of data, or say 64 bits of data each cycle. So you have to do it in chunks, right? So the first chunk contains the first 8 bytes of data, the second chunk, and blah, 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 keep doing it, right? And after you finish writing all the chunks, you can finally request the first chunk and the next block. And then, because the limited bandwidth between your L1 and L2, the missing block finally has to also be returned in chunks in this way. So the miss penalty is more than you can ever imagine. So that's why last lecture we talked about the block size and how bad it is for miss penalty. So this one tells you, right? If you make your block size enormously large, turns out that, well, if you have really good spatial locality for your code, we can eliminate almost every compulsory miss. However, the cost is this. Whenever there is a miss, it takes enormously amount of time to fetch a block as well. So this is not good, right? So a hardware optimization is this: early restart and critical work first. So this is well, I'm talking about the concept of this, not the hardware implementation of this. And the concept of this is trivial. However, the hardware implementation is way more complicated than you can imagine. But the idea of this is that, well, this is the original timing diagram, right? So there's still nothing we can do for write backs at this time. But the basic idea of early restart and a critical work first is that whenever you have a miss, right, and as we said, because your processor only accesses 64-bit of data each cycle, so there must be one word. The word here means 64-bit data. There must be one word that your processor wants at this moment. So the early restart and the critical word first is that we just give you that word first so that your processor can proceed. right? So this is like, let me think about this. How can I get it? Okay, like your Mac or my Mac, right? There is some parts that is broken, but some of the parts that are more critical. So for example, the motherboard is more critical, but the touchpad is probably not that critical, right? So I told the genius guy, the guy's engineer bar, saying that, well, I need this one to work immediately. What can you do? Okay, I'll give you the motherboard first. I put it in there so that we can take it back. When we got the module for the keyboard and touchpad, we can just come back. Right? So this is like early restart and critical work first, is that we give you what you want first. Of course, for the rest of stuff, you have to retrieve it later. But at least you can start working. Right? So that's the idea of early restart and critical work first. So if the requesting data is already received in a L1 cache, the L1 cache can directly return that word to the processor without having the whole block finished. So that's the idea of early restart and critical work first. So now you might be asking, okay, so now we have that this part happens earlier. Can we also reduce the overhead here? Right. So turns out the write back overhead, we can use another idea called write buffer to solve it. So the basic idea of write buffer is that, again, add a small fully associativity cache between your L1 and L2. And whenever I have data that I want to write back, instead of performing the access to the L1 cache, which require you to go through the small, slow bus with limited bandwidth, as well as the slow access time of L2, because L2 is typically larger. We write your stuff first back to this small write buffer and fetch the block from the L2 in the meantime. And so what would happen is that whenever there is a miss, if we need to write, let's write to write buffer first. And remember, this is a small fully associativity cache, so the access time is short. So this is also similar to something you should learn from Noam Jovi's paper, that fully associativity cache is slow. However, if you make it small, it could be efficient, right? So now, after we write back the whole thing to buffer with shorter period of time, you can fetch the block, and this part, again, you can use early restart and critical work first. And simultaneously, whenever your L2 cache is free, the write buffer can present that write back to the lower level memory hierarchy. So in this way, you can see that we make this part of the overhead smaller as well. Or say you can offset this part of the overhead to a later. So this is the idea of buffer. And is that perfect? The answer is no, because sometimes, right? Sometimes we can do even better, right? So, so the thing is that sometimes, right? When you are writing, you're not just writing to one block, one word in a block, right? And there are cases that you continuously update data within a cache block, right? So once in a while, like especially when you are doing things like accumulation, right? You are going to update the data within a block frequently, right? And if you write back every time, and if every time you only update partial parts of the data, it's really inefficient. So the idea of write buffer can also combine with the idea of write merge, is that when I'm doing a write back, if I also found that the block is, so sometimes, right, we don't write back the block immediately. Instead, if we find that the block is still in a cache, we will perform. You find a stuff. So you can return that block that you modified from the right buffer first if you need to write it again. And the thing is, and the second thing is that because of that, you don't write to L2 all the time. Right? So you can treat the write buffer as another victim cache in some sense, and perform the updates there. Perform and perform updates there, so that you don't have to always update to L2 in this way. So this is another thing that you can do with write buffer to better improve your cache performance. Okay, so these are the idea of hardware optimization. So again, this is a computer science class, so I won't dive into the detail how to implement those. But one thing I do want you to think through is that among these techniques, how many of them can help improve miss rate? This question you might need to check your choice. I think one of the previous lecture we accidentally, I mean, the everywhere, the poll everywhere. So you might want to change your decision. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so for this question, I think we need some more discussion among you guys. So why don't you go ahead, 90 seconds.
So you've done and we can work. That's all. So that's why. Yeah, I think it is because
All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so this is after discussion. Okay, still needs some whole classroom discussion, right? So look at the first one. Well, can some of you comment on this one? Is this going to help improving miss rate? But it helps.
Doesn't it reduce hit time?
It just reduces the what?
Hit time?
Hit time or the miss penalty.
Oh,
Right?
okay.
So yes, right? So this one, because it makes the cache non-blocking, so if your data is in a cache, you can retrieve it earlier. Or on another thought is that, okay, when I have a miss on the lower level memory hierarchy, it takes less time for me to get the stuff back as well, right? So this one is helping for the case of when you have a miss, when you have an access, but if it's a hit or miss, does it affect? It doesn't affect if the data is a hit or miss, right? So this one doesn't help. How about this? Critical word first, every early restart. No, right? This one neither, right? Because it just makes your processor return to work early. How about prefetching? Yes, right? So what's the idea of prefetch? Issue the request earlier so that you can eliminate what type of miss. Compulsory miss. So it does help improving cache miss rate. So when we say improving miss rate, it means that the miss rate needs to be lower. So some of you, so recently I learned that the e-learning system allow you to comment on things. However, when you make a comment, it doesn't alert me. So if you have any question, you want to ask through the comment, I won't see it. So, but recently when I reviewed one of the quiz, some of you asked about, the description of the question is vague because it said improve cache miss rate. However, when we say improve cache miss rate, it means the cache miss rate is low. So this is something that I don't think is a vague. Like when we say improve your grade, you know your grade is higher, right? So this is a pretty convention. This is a very well-known convention. Okay, so it does improve miss rate. How about right buffer? How about right buffer? This one neither, right? So right buffer allows the write back to perform faster. But whether or not it will trigger a write back, or whether or not it will be a miss or not, that's not something write buffer can help. So write buffer neither. So the right answer of this question is actually only one thing right. One thing right. Okay? That's why we're playing that. All right. So, okay. So for now, right? So the only thing that would help is right. Sorry, prefetch. All right. So now we have a summary, right? For prefetch, compulsory miss, write buffer, bank pipeline miss penalty, critical word first, early restart. They are all about miss penalty. So you see, for hardware techniques, we have talked a lot. Only one of them can improve miss rate. And you know, whenever you have a miss, your processor already needs to pay some overhead. So if you really want to improve cache performance, the key is that you have to reduce the cache miss rate. So what are the most efficient techniques to reduce miss rate? Turns out the source of high cache miss rate are mainly coming from EO return programs. So it's more important that as a programmer, you have to know what are the good behavior to improve your cache. But before that, Let me ask you some basic C programming question. For this one, what's the output?
x86 or for example, it is 32-bit architecture or 64-bit architecture.
I don't think it matters. This is C programming language, so what the C programming standard said. Well, actually that does. Assuming it's a 64-bit processor. Yeah, 64-bit processors. 64-bit processors. All right, looks like most of you have an answer. So let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, why don't you go ahead and discuss with your friend and see if that changes your mind. You got this.
You have to know.
All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. Okay, after discussion, still 24 of you think the answer is C, meaning it's 32. And here, I just want to let you know, if this is a Google interview question, only this part of people, only 8 of you pass. What? What? If you don't believe me, if you don't trust me, let me run the code for you. We have the demo, right? You know, I really hate this keyboard. But comparing with the keyboard, I hate the new Mac design more. Okay. So look at this, right? So this is the proc.c, right? This is ID, participation, homework, midterm, average. This is exactly, well, sorry. This is what you will see. Let me see. Okay, this is the question, right? Look at the question. This is the question, ID homework, participation, midterm average, right? ID homework, participation, midterm average, right? For this pieces of a code, we did nothing, just print out the size of the struct, right? So let me, okay. Okay, that's print 40. Some of you think about compiler optimization, 40. Okay. But if you do this, in this way,
No. All the order of the declaration.
I just changed the order of declaration. 32. 32. What?
It's because it's
What?
empty slash side.
Come on, you guys.
It's gonna be
You should probably revisit your freshman C programming language class if you don't have one. Then this are, I will feel like this is a very basic thing that every programmer should know. But unfortunately, I don't feel teachers who taught you the programming language or other computer architects would tell you about this. But this is so important, right? Like a lot of times when we design our data structure, we just randomly put our elements in a struct, and we think there are a total of 32 bytes of data. So it should just occupy 32 bytes of data. But turns out that if you lay out data in this way, it actually takes 40 bytes. And here's the reason. Because for, again, you have to know the hardware. And for 64-bit machine, there is a convention for instruction is that for every data structure, it has to be aligned. So if an instruction accesses an object of size n and address x, the access is aligned if x mod n equal to 0. So it turns out that what happened is that if I am accessing double, which is 8 bytes of data, the address of a double must be a multiply of 8. Must be a multiply of 8. So what would happen here is that, right, look at this. Although you think we can make the homework like something like this shape, right? But if you make them in this shape, it will be break up into 2 different units of work in a 64-bit machine.
why can't the compiler just fix that?
I show you. The compiler cannot fix that.
But it doesn't ruin like the structure of the code.
It ruins the structure of the code. Because when your compiler has to reorder the elements to make this access one, right?
Yeah.
And when you declare a structure, that's a convention shared by many other source files that can be linked later, and everyone sees the same header file. They thought this is the order, right? And if you change the order by the compiler, that just creates bugs, right? So the compiler can never do that. Compiler can never do that, right? So here's the thing, right? You have to know hardware architecture. So this is the first lesson I'm teaching. Right? Carefully lay out your data structure. And see, just change the order in your data structure. It improves the size of data, which also implies that you can potentially reduce the capacity or conflict. And that's a very basic thing. And as a software programmer, if you're not aware of that, it will create many inefficient code like that. Now, well, we have 2 different choices of creating our objects. So now, thinking that I am the IT for UC Riverside. and I want to create a spreadsheet or a database that records every item of our students. So from the object-oriented programming perspective, I can do array of objects, which means I am having arrays of objects in which each object contains the records of each student. So for example, each structure is essentially the ID of a student, all the homework item, and the average. Another thought is that we create 3 different tables. And these 3 different tables are combined into a big object. And this object has an ID array, has a 2-dimensional homework array, and an average array. So the layout looks like this in a map. So now, I am having a code which I want to calculate the average of a certain item across all students on campus. Right? Because I want to know if this class is too hard or this class is too simple. Right? So, and I want to generate some insights about how students are doing in this class. This is what I will do. So based on these 2 data structures, I would write code differently, like the left-hand side. So now, which one is better in terms of performance? Just A and B. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Wow. We have a large amount of you think it's B. So why don't some of you just let us know why do you think B is a better option? Because this seems more non-trivial. So you think for this class, the answer must be B. Any thoughts about this? Why is B? So quiet. Okay, let's run it first. While you are thinking, all right, so I have this demo as well. Should be here, structure. So I have this code called array of objects. Right, for this phases of a code, this is the records for each the record for each student, and let's say total number of students and average, and if student average, total number of students, counting average for each student, counting average for each homework, right? So we have 2 pieces of a code, and student average equal to 1. Okay, so now this is what we are going to do, right? So if we have for this program, saying that we have this amount of students, and indeed UCR has this amount of students, and assume that each student you have to finish 10,000 stuff to graduate, and we want to calculate the average of this 10,000 stuff. and how much time it takes to run an average with array of objects. An array of objects, if you took any object-oriented programming before, this is probably the best practice, make your code easy to understand. So it turns out, well, array of objects on these items take 11 seconds. So now, let me do this with, what's the other? I cannot tell you by how much I hate this keyboard, but not sure if there is anyone in Apple heard that. I need a new computer. That's the butterfly, yes. Okay, so this is object of arrays. Wow, damn, right? Ugly code, faster, right? So the thing is that, right, sometimes software programmer, when you design your data structure, you are not coming from the performance perspective. You're just coming from the fact that it's more human readable. But sometimes when you go into the company, you figure out there are some magic code that people don't like to change. There's a reason for that, right? Some of the engineering stuff cannot be completely judged by the principles that you learn from software engineering. And the thing is that if you go that way, sometimes it's a disaster. So, but the thing is that there is not an always win between these two data structures. So for example, my criteria is that what I just mentioned is that I want to, the use case I want for this database is that I want to calculate the average of each homework. But what if today, my perspective is that I'm more interested about how each student learns. So it turns out that I want to calculate the average of each student. So for the same program, which you can check out the source code later on our GitHub, is that if I want to do average for each student, here is object of arrays. And if I want to use array of objects. Yeah. Hello. Still slow, huh? Wait, is it true? Okay. Okay, I guess for array of objects, the right thing to do is not putting a parameter up there. The program is broken somehow. But here's the thing, right? If all you want to do is calculate the average of each student, array of objects is actually a better option. Right? So what really matters is that as a programmer, you have to figure out what's the common use case of your algorithm. So turns out that in many of the database fields, people know that we are going to use this kind of a column sum or column operation more often than the row operation. So it turns out that many database systems, they are designed in a way of column store instead of row store. So you might think if I have a table, like if in Excel or in a database system, if I have a table like this, right? I have a row ID 110 Smith, Joe, 40,000, right? Then you might think, well, it's intuitive for you to store this data on a disk. But actually, most of the database will store them in a column store order in a way that we store things like this, we store like 10, 12, 11, 24, Smith, Jones, Johnson, Jones, right? Like this. This is what we actually do in database. So in database system, it takes the design in a way that, yeah, we know we are our workload is more on column accesses, column operation. And think about this, right? I believe most of you have experience of using SQL. Every time when you do SQL, what do? Select block, column, block, column 1, column 2, column 3. Right? So it turns out, if you look at the frequently used pattern in SQL, it already tells you that we want columns to be accessed together more often than having each record, all the data from the same record to be looking at together all the time. So this is an example that software engineering tell you from the object-oriented perspective, you should attach the properties of, to each individual or each element. However, from the performance perspective, that's not always the right thing to do. It's more important for you to figure out what's the common use pattern and design data structure to that. So database chose column store most of the time. If you don't know why, thinking about what's the most commonly used SQL query in your life. Select column 1, column 2, where a column equal to something, right? It's all about columns, right? And even when you see equal to something, it's all about columns as well, right? So why don't we just do column store to make the whole thing more efficient? So the second tip is that being a software programmer, be aware of what's the common access pattern so that you can potentially improve confidence. All right. Now, another technique is called loop interchange, fission, and fusion. So for loop interchange, you must already learn those before, right? Like when we add two elements together, and now you know because our cache is favoring spatial locality, and in C programming language, neighboring items means that the lowest rank of the index will be stored in sequential addresses. So if you can traverse your data in that way, it's going to be more cache friendly, right? Even though both algorithm has the same complexity, but you have to make your algorithm implementation more cache friendly. So that's one example. And another example, which we discussed before, is the AMD processor. For this pieces of code, as the programmer, you can actually fix it. So let me, and here is my solution. But what I want you to do is that for this solution, by how much we can improve the cache. So why don't we wrap up in 15 seconds? Five, four, three, two, one. Time is up. Okay. Ta-da! Okay, here's the answer that you guys thought. So why don't you go ahead and discuss with your friend for another 90 seconds and shoot me an answer. Your voice, your energy.
Yeah, it should be.
All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. After discussion, most of you still think it's B. And you know, sometimes majority is not right. You learn it once before, right? Today. So sometimes, like when we have the midterm, don't cheat because it sometimes hurts you, and most of the time it does. Okay, so for this specific question, again, for this type of question, what was the first thing to do? What is the first thing to do?
Oh, C equals ABS.
C equal to ABS, and what's the purpose of that? Partition of your address, right? And so to partition what address? The address sequence that you are going to access. Right? So for this particular piece of code, what is going to be the first address then? A0, right? Like if you look at this, right?
Oh.
Yeah, you have to get A first and then store it to C,
Yeah.
right? So first of all, you have C equal to ABS and then load A0. Here's the address of A0. Partition it, you get a tag, index. This is the miss, you know this, right? And the next one will be the C, right? Remember in a previous version, a single loop, we have both A and B add together and C. But now we only assign A to C. And this is the address of C, miss, right? What's next?
A1.
A1, right? When we access A1, when we partition this, it don't miss. It, right? Same thing for C1, it's going to be a hit. And remember, if you put in, if originally your code is written C, B, that will be misses, right? And you keep having this pattern until you meet A16, right? Because each cache block can only accommodate 16 integer elements, right? So then the same pattern repeat until the end, right?
That's the first loop. Now, for the second loop, we already have the values of A. Now, you do an equal plus equal BI, which means that you will load the content of B, load the content of C, add them together, store them to C. So you have 3 memory accesses. But these 3 memory accesses are on B and C. Right? So what happened is, first of all, you are going to load B, and this is the first time in our code using B. Right? So here there must be a miss. How about a C? So that's a little bit tricky here. So we have 64 kilobytes of data that you can store in the cache. And you have two-way associativity. And this array is well sequential, serialized, right? So if you think about the hash algorithm we use, sequential addresses, sequential blocks, they should spread out, evenly spread out. So in this case, we can think if your array is smaller than 32 kilobytes, they can all be kept in the cache. Agree with that? Because you have 2 ways. So it's very likely one cache array is for array A, the other cache array is for array C. They are all together. Okay. So what happened here is, and if you look at the data structure, this is what? This is 16K. And each of them. Okay, so this is times 4. Because each integer is 4 bytes. So turns out that would be larger than the cache capacity. Right? Okay, so my answer is wrong. So here for C, this one is actually going to be this. Because very likely it's going to be kicked out at some point. Agree with that? Okay, so, but after this miss has been served, the rest of the accesses will be hit, as the pattern you see here. Agree with that? C1 will not be a miss, right? Because for C1 it's in the same block as C0. Right? So turns out for the first loop, you will have this amount of accesses, this amount of misses. And for the second loop, you will also have this amount of misses. So there will be a total of 512 times 5 accesses, and a total of 512 divided by 16. That's the frequency of also in the first 3. But here we also have capacity, right? Because now your data structure is 64 kilobytes. Your cache also 64. So one of them will be capacity. So you will have this amount of misses. So it turns out the right answer will be you will have 512 divided by 16, this amount of misses divided by 512 times this amount of total access. Total 1, 4, and this is the actual cache miss rate, about 5%. So because 5% is right in the middle of A and B. So if you choose A or B, they are both correct in this way, right? So yeah, but after going through this example, I think you have a better idea how we get this cache miss rate. So for this example, you can see, whoa, what happened? Originally, this piece of code, we have 100% miss rate, but now
if your programmer is smart enough, you can make it a very low cache mismatch. And this is not something that a compiler can do with you. Okay? All right, so yeah, I will fix that. So this technique is called loop vision because it's typically separate one loop into two. And again, from the algorithm perspective, that's not intuitive because most of the time we think, well, if we can put one thing in, or if we can put everything in a one single loop iteration, it's more human readable, it seems more elegant, and people will say, well, what a beautiful code, right? But if it's an AMD processor, it will say, what a disaster, right? So that's the thing, right? But when to use loop fusion? But another thing is like, is that always good? So for the same pieces of code, right? If you do this in Intel process, which works well for C equal to A plus B, right? Doing loop fusion, as you can see, the amount of cache accesses are actually increasing, and you are not going to get any benefit of improving of cache miss rate because cache access still takes time. So turns out that loop fusion means that if we have two separate loops, we combine them together. It's the opposite of loop fusion. So it turns out that when you use loop fusion, it completely depending on what kind of processor that you are interacting with. So if you are interacting with a processor with fewer ways of cache, very likely those embedded system processor, then loop vision is probably a practice you have to take. However, if you are interacting with processors that are manufactured in a better process technology, like Intel processor or modern AMD processors, loop fusion is probably a better practice because it reduces the amount of memory and you don't see any drawback on the cache hit rate. So the thing is that the third practice, which I want to let you know today, is implementing algorithms in a more cache-friendly way. All right. So this concludes our lecture today. But in the next lecture, I'm going to continue this discussion by giving you a comprehensive example of how can we use this technique to implement a larger scale program instead of just a few code snippets. But before you leave the classroom, there are still a few things that I want to let you know. There is one more reading quiz due next Monday, and there will be assignment 2 announced later today, which I'm still thinking about what's the right question to put because I'm running out of idea. If you have any idea what to put in a homework, let me know. And also we have office hours, which we know that the lecture time is short, it's precious, so sometimes we optimize the class flow to for the majority. So like when I count out this reading quizzes, I'm basing on how many of you have clicked the answer. So typically, whenever we have 75% of you answer the question, and I definitely count who is here, and it's well, and I know this is October, Halloween is coming in, so sometimes we have more people than we actually have here, which I don't know why. Well, probably people from YouTube, I guess. So, but that's how I count. So if you sometimes you take more time and if the discussion later on doesn't help you address those issues, office hour is where you can find solution you can discuss with us. Other than that, enjoy the rest of the day, enjoy the rest of the week. I will see you later. What? Still next Wednesday. Yeah, we still have a week.
Okay, perfect. Have a nice day.
You too.
I want to understand that simulating the cache memory is more better. So, is there a way that I can like
I would say practice.
practice?
Yeah, so that's why we have the homework.
Okay, so it's part of the next homework.
Yeah, it will be part of the next homework.
Okay, and anything I should like read up? Or...
So I would say just follow the stage that we walked through, right? Partition the address and generate a access sequence. And typically, if you understand the code well, you should be able to know that. Yep. All right.
I always approach it off without
Sure.
I got the question about the optimization of the AMD code.
Sure.
So the only way